Hello, today we're going to be going over implicit differentiation. But before we start with implicit differentiation, let's go back and revisit the normal format that we've been taking of basic functions. That format looks something along the lines of y is equal to x squared plus b. This could be a function for a line. It could be just an exponential function, y equals to x squared, a parabola, something like that. However, there are times and there are functions that we are going to have to know how to take the derivative of in the future. For example, a circle, right? A circle has the function and equation of y squared plus x squared is equal to some constant. However, this right here, we cannot just apply basic product rule, chain rule, power rule. All of that cannot be applied to this type of function because whenever you take the normal derivative, it is always in terms of x. And as you can see here in this equation, we have a y term that we have to take the derivative of, and that we cannot simply use this for. So, how do we actually solve something like this? We have to take implicit differentiation of both sides of the equation. And what implicit differentiation means is when you take the derivative of a function and each term gets treated independently with respect to its own variable. So let me show you what that means. So let's just look at this y squared term. So if we want to take the derivative with respect to x, which is what we have been doing, of y squared, this equals to the derivative of y squared, which is just 2y, times dy dx. Now, this dy dx says that we have taken the derivative of y with respect to x, because the entire format has to be here. And now we have two more variables in the equation. We have this dy, and then we also have this dx, which you can think about them as constants almost, as your new y's. So y is now dy, x is now dx. So let's look at an example. We have x squared plus y squared is equal to 25. So first thing we do, so step one would be to differentiate both sides with respect to x. So it would be d dx of x squared plus y squared is equal to d dx of 25. We know that a derivative of a constant is just 0. So this side goes to 0. This side we can distribute the d dx. It would be d dx of x squared plus d dx of y squared. So step 2, it would be to take the derivative, and again we've kind of already taken the derivative of this side, but let's focus just on the x's. So the derivative of x squared would be 2x. And another way we can think about this to make it a bit easier is whenever you take the derivative, the variable that you took the derivative of, so in this case x, you multiply it by the numerator. You make that the numerator. And then the denominator is what the derivative was with respect to. So we took the derivative with respect to x. So d dx, now I'm going to keep it in blue, comes to the denominator. And this x was because this variable x is what we took the derivative of. So why that is important is because whenever you take the implicit differentiation of another variable, say y squared, right? I'm going to take this and move it in a different line. So d dx of y squared, and actually we already solved that up here. So we are taking a derivative of our y. So this y variable is the same as what we multiply up top, but the derivative is with respect to x. So whatever the with respect to is in the bottom, whatever variable we just took the derivative of is on top. So let me just write that out clearly. So whenever you take the derivative of something, multiply it by d of variable that you took derivative of over, I'm going to make this red, d variable with respect to. And with respect to just means derivative with respect to x. So this applies to every single type of derivative, this note. So going back to this, I'm going to rewrite that. So we took the derivative of this right here. So now we have 2y, and then up top becomes our dy, because this was the y, over dx, because we're taking the derivative with respect to x, is equal to 0. So now we can see dx over dx here just cancels out. So we can rewrite this as 2x plus 2y dy dx is equal to 0. So what are we trying to solve? This right here, the dy dx term, because how it comes from this right here, this is your implicit differentiation. Implicit means multiple variables. So we have taken the derivative of the whole equation. We are trying to isolate this term. So let's first start off by moving the x to the other side. So we have, so many colors. We have 2y dy dx is equal to negative 2x. Divide both sides by 2y, which gives us dy dx is equal to negative 2x over 2y is equal to negative x over y. And that is our final answer. So what that actually means is the implicit differentiation of this equation right here ends up being negative x over y. And this demonstrates that the slope of the tangent line to the circle, because remember, this equation is the equation of a circle. The tangent line, because derivatives tell you the slope, the tangent line at any point of this circle is this slope right here. That's what that means. And I know that's a bit complicated wording wise, but again, remember, derivative is your slope and the slope of the circle. So if you have your circle at any point on the circle, this is your slope.
All right, hope that made things clear.